The Woodward Hoffmann rules, devised by Robert Burns Woodward and Woodward Hoffmann, are a set of rules in organic chemistry predicting the barrier heights of pericyclic reactions based upon conservation of orbital symmetry. The Woodward Hoffmann rules can be applied to understand electrocyclic reactions, cycloadditions including keeltropic reactions, sigmatropic reactions and group transfer reactions. Reactions are classified as allowed if the electronic barrier is low and forbidden if the barrier is high. Forbidden reactions can still take place but require significantly more energy. Due to their elegance and simplicity, the Woodward Hoffmann rules are credited with first exemplifying the power of molecular orbital theory to experimental chemists. Hoffmann was awarded the 1981 Nobel Prize in Chemistry for this work, shared with Kenichi Fukui, who developed a similar model using frontier molecular orbital or FMO theory. Because Woodward had died 2 years before, he was not eligible to win would have been his second Nobel Prize for Chemistry. The Woodward Hoffmann rules were first invoked to explain the observed stereospecificity of electrocyclic ring opening and ring closing reactions at the termini of open chain conjugated polyenes, either by application of heat, that is thermal reactions, or application of light, that is photochemical reactions. Now, in the original publication in 1965, the three rules distilled from experimental evidence and molecular orbital analysis appeared as follows. In an open chain system containing 4n electrons, the orbital symmetry of the highest occupied orbital is such that a bonding interaction between the termini must involve overlap between orbital envelopes in opposite faces of the system, and this can be achieved only in a conrotatory process. In an open system containing 4n plus 2 electrons, terminal bonding interaction within the ground state molecules requires overlap of orbital envelopes on the same phase of the system, attainable only by disrotatory displacements. Now, in a photochemical reaction, an electron in the HOMO of the reactant is promoted to an excited state, leading to a reversal of terminal symmetry relationships and reversal of stereospecificity. The Woodward Hoffmann rules can also be derived by examining the correlation diagram of a given reaction. A symmetry element is a point of reference, usually a plane or a line, about which an object is symmetric with respect to a symmetry operation. If a symmetry element is present throughout the reaction mechanism, the reactant, transition state and the product, it is called a conserved symmetry effect. Then, throughout the reaction, the symmetry of molecular orbitals with respect to this element must be conserved. That is, molecular orbitals that are symmetric with respect to the symmetry element in the starting material must be correlated to or transform into orbital symmetric holes for anti-symmetry with respect to a conserved symmetry element. A molecular orbital correlation diagram correlates molecular orbitals of the starting materials and the product based upon conservation of symmetry. From a molecular orbital correlation diagram, one can construct an electronic state correlation diagram that correlates electronic states, that is, the ground state and the excited states of the reactants with electronic states of the products. Correlation diagrams can then be used to predict the height of transition state barriers. Using correlation diagrams, one can derive the selection rules for the following generalized classes of pericyclic reactions. Each of these particular classes is further generalized in the generalized Woodward Hoffmann rules. The more inclusive bond topology descriptors, that is antifacial and suprafacial, subsume the terms conrotatory and disrotatory respectively. Antifacial refers to bond making or bond breaking through the opposite face of a pi system, p orbital or sigma bond, while suprafacial refers to the process occurring through the same face. A suprafacial transformation at a chiral center preserves stereochemistry, whereas an antifacial transformation reverses the stereochemistry. So, after studying this module, you shall be able to know what are Woodward Hoffmann rules, learn how to draw correlation diagram for various pericyclic reactions. Thirdly, identify the fundamentals on which Woodward Hoffmann rules were founded, evaluate the course of different pericyclic reactions based on Woodward Hoffmann rules, and analyze practical examples of Woodward Hoffmann rules. Let us start by the introduction. Pericyclic reactions are a set of reactions with unique features such as concerted mechanism, no or little effect of solvent polarity, no reaction intermediates, high degree of stereoselectivity and stereospecificity, and only means to bring about the reactions are thermal and photochemical. Molecular orbital theory helps to understand fundamentals of pericyclic reactions. Electrons in an atom are associated with wave-like and particle-like character. As a wave, the electrons are defined by a wave function psi. Square of psi gives the probability of finding electron in a given space which is close to the definition of an atomic orbital. Comparing the motion of electrons with standing waves, the atomic orbitals, that is AOs, are defined by parameters such as amplitude, phase of wave and a nodal plane. Linear combination of atomic orbitals of comparable energy gives molecular orbitals abbreviated as MOs. The number of MOs formed is equal to the sum of the AOs. Thus, for ethylene, two MOs, namely pi and pi star, arise from the combination of two p atomic orbitals, as shown in the figure. The lower energy being the pi bonding MO and the higher energy being pi star anti-bonding MO. Similarly, in butadiene, the combination of 4 atomic orbitals gives rise to 4 molecular orbitals, namely psi1, psi2, psi3 and psi4, and so on for higher systems. The importance of considering the phase of orbitals is due to the fact that only orbitals with same phase combine together to give rise to bond formation. Now let us have a look at correlation diagrams. The frontier molecular orbital theory, or the FMO theory, is a simpler way to look at the molecular orbitals of a conjugate system based on highest occupied molecular orbital, abbreviated as HOMO, and one component and lowest unoccupied molecular orbital LUMO of the second component in a pericyclic reaction. These are the closest MOs in terms of energy and make a significant contribution to lowering of transition state energy as they interact. HOMO and LUMO of any given compound have opposite symmetries. HOMO and LUMO are referred to as frontier molecular orbitals. Thus, bonding takes place when lobes of equal phase on two different molecules overlap with each other. You can see in the diagrams, the first is a 2+2 cycloaddition reaction where the LUMO are interacting with the HOMO. Not being in phase results in repulsion. The second example is a 4+2 cycloaddition where orbitals in the same phase are interacting. New molecular orbitals are thus generated by linear combination of atomic orbitals. Linear combination of orbitals is also known as perturbation molecular orbital theory, abbreviated as PMO. Linear combination always takes place between two orbitals, two atomic orbitals, two molecular orbitals, or one atomic orbital and one molecular orbital, having minimum energy difference. This implies that one needs to consider only at the result of the pi plus minus pi and pi star plus minus pi star interactions and do not have to consider pi plus minus pi star, as these are too far apart in terms of energy. The correlation diagrams are used to identify preferred reaction pathways or experimentally observed products for a given set of molecules. Correlation diagrams use elements of symmetry as a guiding rule, which should be preserved throughout the reaction. It is assumed that an orbital in the starting material must feed into an orbital of same symmetry in the product. Therefore, if the number of orbitals of each symmetry type is not the same in the reactants as in the products, that reaction will not take place readily. There are various steps to build a correlation diagram. For example, let us build a correlation diagram for a thermal 4+2 cycloaddition and examine feasibility of the reaction. Step 1 involves to draw the backbone of reaction and drawing the curly arrows for the forward and backward reaction. It is assumed that substituents do not perturb the symmetry of these reactions. The dotted line shows the plane of symmetry of the products and the reactants. Step 2. To identify orbitals that undergo change in both the reactants to give the product and in the product for reverse reaction. In this case, for forward reaction, these are the pi orbitals on both the reactants. Step 3. To identify the symmetry elements maintained throughout the course of the reaction. For the reaction under consideration, we have only one element of symmetry, that is, a plane of symmetry dissecting the C2 and C3 bond in the diene and the pi bond in the dienophile in the diagram. Step 4. Keeping the reactant at the left and product at the right hand side, drawing MO in increasing order of energy. Step 5. Drawing orbitals besides each energy level, including all the bonds involved in the reaction. For the forward reaction, we will have a total of 6 pi MOs, 4 from diene and 2 from the dienophile. For the reverse reaction, involvement of 6 sigma bonds is evident and we will have a total of 6 MOs, this time 4 sigma and 2 pi, which also give rise to bonding and anti-bonding orbitals. Step 6. Classification of orbitals with respect to symmetry element. On the left hand side, the lowest energy orbital, psi1, belongs to the diene with no nodes. It is symmetrical based on mirror plane symmetry element. Moving up, the next orbital is pi bond of the dienophile, which is also symmetric with respect to mirror plane. Next higher orbital, energy orbital psi2, is antisymmetric, as when the mirror plane divides the orbital into two halves, the two sides are not mirror images of each other. Based on the sign of lobes, all other orbitals are divided as symmetric and antisymmetric based on the mirror plane symmetry element. As you can see very clearly in the diagrammatic representation, the dotted line represents a plane of symmetry which intersects the page here. Step 7. Construction of orbital correlation diagram. We started with the assumption that orbitals in the starting material must feed into an orbital of same symmetry in the product. Therefore, we now draw lines to connect orbitals with comparable energy and same symmetry on the two sides. Thus, lowest orbital on reactants, that is psi1, with S symmetry on the left connects with the lowest energy sigma having S symmetry on the product at the right hand side. Pi S connects with pi S and psi2a connects with sigma 2a and so on. In step 8, that is the last step, is construction of state correlation diagram. The ground state, that is GS orbital in reactants, goes smoothly into the ground state orbitals of products. Thus, filling of 6 electrons in the lowest energy orbitals gives ground state designation as psi1 2, pi 2, psi2 2. As all the terms are squared, the state is said to be symmetric. Similarly, the ground state of product has a designation of sigma 1 2, sigma 2 2, pi 2, which is also symmetric. Thus, as the individual orbitals of the ground state in the starting material correlate with the individual orbitals of the ground state of the product, the correlation diagram consists of a line joining the ground state with the ground state. Now, let us make correlation diagram for a forbidden reaction and try to see what happens. Considering 2 plus 2 thermal cycloadditions, we have 2 ethylene molecules as reactants and so 4 pi electrons to fill the orbitals. Additionally, here we have 2 planes of symmetry to consider as shown. The first plane bisects the sigma bond in the middle and the second plane lies between the two dienes as they approach each other for bond formation. In the correlation diagram, the lowest energy orbital on a reactant, pi 1, is symmetric with respect to both planes as it is designated SS. The next higher energy orbital is anti-bonding combination of pi 2, which is symmetric with respect to one plane but antisymmetric with respect to the second plane. So, it is designated SA. Similarly, the rest of the orbitals are classified as symmetric and antisymmetric. Now, correlation diagrams can be constructed by feeding the orbitals in the starting material to orbitals with the same symmetry and comparable energy in the product orbital. In the state correlation diagram, the ground state of the starting material pi 1 2 pi 1 2 is overall symmetric as both the terms are squared. The ground state of product sigma 1 2 sigma 1 2 is also symmetric. However, in the correlation diagram, since the states of same symmetry crossing each other, the bond formation would require very high energy to overcome the symmetry barrier as shown in the following state correlation diagram. The state correlation in this case comprises of excited state transitions which become possible if electrons in the reactant are promoted to the first excited electronic state, that is from pi 2 to pi 3. Thus, the first excited state for reactants becomes pi 1 2 pi 2 pi 3 star. Following the lines from the correlation diagram, now we have one filled pi 1 2 SS and two half filled pi 2 pi 3 stars SA and AS. Joining to sigma 1 2 sigma 2 sigma 3 star, which are SS, AS and SA respectively, without crossing similar symmetry states. Thus, in the first excitation state, the bond formation becomes possible, and this is the reason why photochemical 2+2 cycloaddition is feasible. The Woodward Hoffmann rules were derived from the conservation of orbital symmetry seen in the correlation diagrams. There are, however, secondary effects due to subsequent effects on rates and regioselectivity of reaction that may alter the fate of a pericyclic reaction and provide some anomalies like endo rule for Diels-Alder reaction or torquoselectivity. Here we shall briefly look at Alder's endo rule only to emphasize on the factors other than symmetry that might as well influence the regioselectivity of a cycloaddition reaction. In the reaction given, maleic anhydride reacts with cyclopentadiene by way of an endo transition structure. The exoadduct is formed only in very little amount. This preference of formation of endoadduct, which is kinetically controlled, is called Alder's endo rule. This effect was explained based on the FMO approach and visualizing the transition state for orbital overlap. As you can see in the diagram, other than the primary bonding interactions by orbital overlap, there are additional secondary bonding interactions between the two reactants in the endo transition state, thus favoring endo product over the thermodynamically more stable exo product. Now let us have a look at the application of correlation diagrams and the Woodward Hoffmann rules. Based on the rules of conservation of orbital symmetry, that is correlation diagrams, Woodward and Hoffmann were the first one to deduce a set of rules to define feasibility of reactions and stereochemistry of products formed in pericyclic reactions. According to Woodward Hoffmann rules, the reactions in which symmetry of molecular orbitals, that is MO, is conserved involve a relatively low energy transition state and thus are symmetry allowed. In contrast, in the reactions where symmetry of orbitals is destroyed by bringing one or more orbitals out of phase, the energy of transition state becomes too high due to an anti-bonding interaction and the reaction becomes symmetry forbidden. Another important foundation of the rules is the fact that thermally allowed reactions are forbidden photochemically and vice versa. Also, the products formed as a result of thermal tractions have opposite stereochemistry than products of a photochemical reaction. It is important to note that symmetry forbidden reaction might as well proceed if sufficient energy is provided to the reaction. Now that shows the Woodward Hoffmann selection rules for pericyclic reactions. Let us now summarize this module. Pericyclic reactions are a unique set of concerted and stereospecific reactions that take place without an intermediate. According to the MO theory, molecular orbital theory, effective overlap of same phase of atomic orbitals gives rise to bond formation. According to frontier molecular orbital theory, FMO, HUMO and LUMO of the two components in a pericyclic cycloaddition reaction have a major contribution in lowering of the transition state energy, thus are apt to be considered as most important orbitals. The linear combination of atomic orbitals of comparable energy gives rise to molecular orbitals. Correlation diagrams are used to identify the preferred reaction pathways and stereochemistry of pericyclic reactions. Correlation diagrams take into consideration the orbital symmetry as a guiding principle. An orbital in the starting material must feed into an orbital of same symmetry in the product. When two states of same symmetry cross each other in a correlation diagram, the reaction is said to be symmetry forbidden and requires large amount of energy to go forward. Woodward Hoffmann rules are based on orbital symmetry conservation.